Hello and welcome to MATLAB programming for numerical computations. We are in module 8. In this module we are covering practical aspects of solving ODE initial value problem. In the previous lecture we extended ODE-45 to a general multivariable case. In this lecture we are going to take up examples where ODE-45 is going to find it very difficult to solve the problems. The reason is ODE-45 is a Rangekutta solver, which is an explicit solver. An explicit solver will have numerical difficulties when faced with what is known as stiff systems. So what I'm going to cover in this lecture is what stiff systems are, and if ODE-45 fails, how you can instead use ODE-15s. What we are going to do is we will first start off with the same problem that we looked at in the previous lecture. So let's go to MATLAB and do that. Okay, so this is the solve mass spring example that we took earlier. What we have done in the previous lecture is this. What we did was we said that the way we are going to write our functions that we are going to use for ODE-45 in multivariable case is going to be exactly same as we did in the single variable case. The only difference is that our y is an n by 1 vector, n rows and a single column, and our fval is also an n by 1 vector, n rows and a single column again. We solved this using ODE-45. Now if we want to solve it using ODE-15s, I can show you how simple it is to solve using ODE-15s. If we were to solve this using ODE-15s, all we need to do is change ODE-45 to ODE-15s. That is all that we need to do. Okay, I click on run. Okay, and I get the results the same as what we had seen before. So take home message over here is that ODE-15s for an external user like us works in the same manner as ODE-45. If ODE-45 works, then why do we need ODE-15s? And the reason for this is ODE-45 may not work for all the cases. So let's go on to PowerPoint and see. Okay. So the cases where we need to look at ODE-15s is what is known as stiff systems. So let's consider the ODE x dash equal to minus 100 multiplied by x1. Okay, we can solve this problem as t sol comma x sol equal to ODE-45 at t comma x minus 100 multiplied by x1, negative 100 multiplied by x. Let's take the t span for this as say 0 to 1, and take the initial value as 1. Let's also plot t sol comma x sol, and let's see what we get. Okay, when we solve t sol comma x sol, we see that the value of x, or rather the value of x1, drops rapidly and goes on to equal to 0. Okay, so within pretty much 0.01 seconds, the x sol value has dropped to its steady state value of 0. Okay, so let's hold this. Now what we will do is we'll consider the other ODE minus 100 multiplied by x. So t sol comma x sol, sorry, not minus 100 multiplied by x, minus 0.01 multiplied by x. Okay, so minus 0.01 multiplied by x is what we need to solve. Okay, and we will plot this result as well. And let's look at the graph. As you can see in the red color line over here, this particular value remains nearly constant at 1. And let's now solve the same problem again, but instead of t span being from 0 to 1, let's make t span as 0 to 3000 and then plot this and see what we are going to get. Let's look at that figure. Okay, as you can see over here, the earlier graph goes from 1 to 0 within 0.1 seconds, whereas the second system goes from 1 to 0, takes almost 500 seconds in order to do that. So when this coefficient is a very large value, the system responds very quickly. If this coefficient is a very small value, then the system responds very slowly. Now the question is, what if the two variables were together in the same equation? If we have dx in the same vector equation rather, if we have dx1 by dt equal to minus 100 x1 and dx2 by dt equal to minus 0.01 multiplied by x2, what we are going to get is this. So if we have an explicit solver such as a Runge-Kutta solver, and we have this system and this system together as shown over here, okay, we need to take really small steps because of this particular equation. The steps that we need to take would be of the order of 0.001. But in order to get the evolution of this particular equation, we need to solve this problem for a large number of time, which means we need to take a step of 0.001 but need to go almost to 100 or 1000 steps. That's the reason why stiff systems are going to be difficult to solve. The reason is we need to take small steps in order to ensure stability, but we want to go to a large amount of time. Let's see what happens when we try to solve this using ODE-45 and ODE-15s. Edit, multi-var fun. Let's create this. Function fval equal to multi-var fun t comma y. We'll do a equal to minus 100 comma 0 0 comma minus 0.01. That's our a matrix, and fval equal to a multiplied by y. Okay, so we have done this. So now let's go and run this using ODE-45. T sol comma y sol is going to be equal to ODE-45 at t comma y multi-var fun t comma y. For t span from 0 to, let's say 0 to 200, that should be sufficient for us to show what we have, and for initial condition of 1 and 1. Okay, and we have run this using ODE-45. Okay, now MATLAB has solved this using ODE-45. Look at the number of time steps MATLAB has taken. It has taken 24,157 time steps in order to solve this rather simple problem using ODE-45. So let's plot t sol comma y sol and see what we are going to get. Okay, this particular guy responds very quickly, whereas this guy is responding extremely sluggishly. Let's look at our vector t solve and see what we get. Okay, so as you can see, our solver is taking very small steps. It started with steps in the order of 10 to the power minus 4, but as things progressed, okay, it could not take large steps. It is still taking steps of the order of 10 to the power minus 3, as you can see over here. The reason why it needs to take steps in the order of 10 to the power minus 3 is because an explicit method will become unstable if we take larger steps. On the other hand, ODE-15s is an implicit method, and there is no restriction on the, or typically there is very small restrictions on the step sizes that ODE-15s will take. So let's try to solve the same problem using ODE-15s. Let's call this as T2 and y sol 2 equal to ODE-15s multi-var fun from 0 to 200, and initial condition is 1 and 1. Okay, and let's solve this and let's plot t2 comma y2. Okay, as you will see, t2 comma y2 has the exact same behavior as tsol comma ysol. Using ODE15s, we are going to get the exact same behavior. However, when you look at the number of points at which ODE15s has run, it has run only at 88 points instead of 24,000 points. Let's click on our T2 and see the points at which it has run. Okay. Initially, when our first guy, our x1 is still evolving, the ODE solver needs to take small steps in order to maintain accuracy. So in order to maintain accuracy, ODE15s has taken small steps, 10 to the power minus 4, 10 to the power minus 4, 10 to the power minus 4. Now it has started taking steps of the order of 10 to the power minus 3. But as we go further, okay, now it has started taking steps of the order of 10 to the power minus 2. We go even further beyond, say, time 2, it has started taking steps in the order of 1. Now it has started taking steps in the order of 10. Accuracy dictates that the steps need to be taken in the order of 10 to the power minus 3 till the response of x1 stabilizes. But after the response of x1 stabilizes, we don't have to worry about x1. We should be able to take larger steps. We are unable to take larger steps in an explicit solver because this is a stiff system, but we are able to take larger steps in an implicit solver, which is ODE15s. So the question is, what is the definition of stiff system? The working definition of stiff systems for this course is going to be: a stiff system is a system where you have a highly fast dynamics and highly slow dynamics coupled together in the same ODE. So question is, does the stiff system needs to be diagonal or linear? So let's take this particular example where A is minus 5.7, 1.85, okay, 13.2 and minus 4.3, 13.2 and minus 4.3. And then let me click evaluate selection so that now we have A. Okay. So now let us solve this using ODE45. Okay, everything else remains the same. We are going to solve it using ODE45. Okay, and when we solve it using ODE45, we see that we take 2400 steps. We now solve it using ODE15s. When we solve it using ODE15s, let's run this using ODE15s and see how many steps ODE15s takes. ODE15s requires only 40 steps. Question is, why is this happening? The reason why this is happening is, let's take the eigenvalues of our A matrix. The eigenvalues of A matrix are of the order of 10 and of the order of 0.01. Okay, so the ratio of the two eigenvalues, ans1 divided by ans2, is a very large number. It's of the order, well, it's actually not very large number, it's a reasonably large number. The ratio of the eigenvalues is of the order of 1000. So this matrix A is an ill-conditioned matrix. We are going to have stiff system and it might be necessary to use ODE15s. Okay, let's look at an example of a nonlinear system. This is a solved example in MATLAB help files. This is known as a van der Pol oscillator. This is the overall equation: x double dash minus mu multiplied by 1 minus x square multiplied by x dash plus x equal to 0. And these are the starting points. Okay, so let's go to MATLAB, edit my VDP. Okay, so function fval equal to my VDP t comma y. Let's call mu equal to 1. Okay, our first guy is going to be dx by dt equal to x dash. So our fval 1 comma 1 is going to be nothing but, so let's call x equal to y1 and v equal to y2. Okay, so fval is nothing but dx by dt, and dx by dt is equal to v, and fval 2 comma 1 is going to be equal to square mu multiplied by 1 minus x squared multiplied by v minus x. And now let's run our tsol comma y sol equal to ODE-45 at t comma y my VDP t comma y. Okay, let's run it from 0 to let's say 10. That should be sufficient, with an initial condition as x0 equal to 2 and x dash 0 equal to 0. So that is our initial condition. Okay, let's solve this, and let's also do plot t sol comma y sol 1 comma all. Okay, t sol all comma 1. So let's do this. Okay, this is our van der Pol oscillators solution for mu equal to 1. For mu equal to 1, van der Pol's oscillator is not a very stiff oscillator, and therefore we get the solution very quickly. So the first practical tip is that when you know that the system is non-stiff, or you're not sure about the stiffness of the system, you should first use ODE-45. If ODE-45 does not work, or if you know that the system is a stiff system, that's when you should use ODE-15s. So let's make the system stiff by changing our mu to 100, and let's try to solve this using ODE-45. Okay, let's solve it up to from 0 to 1000, and let's solve this, and let's see that we'll see that this particular system behaves rather sluggishly. It takes a fairly long time in order to solve. Okay, I'm still waiting for ODE-45 to solve, and finally ODE-45 has solved this. Okay, it has taken almost 2 lakh steps. Let's now solve this using ODE-15s instead. Because this is a stiff system, as you will see that solving this using ODE-15s is going to be much faster, and instead of 2 lakh points, it's going to solve that in only 1725 points, and the result is the same as before. Now if we were to increase the mu to 1000, and this is what your MATLAB help example gives you, if you increase this to 1000, you will not be able to solve this problem using ODE-45. So let's try to solve this using ODE-45, and let's give this. I have waited for nearly 1 minute and it has not yet solved. So let me just cancel this by pressing Ctrl C. As you can see, in a reasonable amount of time, ODE-45 has still not solved this problem. Okay. Instead, if we were to solve this using ODE-15s, we are going to get the solution fairly quickly. Okay. Let me solve this, say up to 40 span equal to 5000, and then I'll show you why this is an extremely stiff system. As you can see, the system responds slowly at first till a certain point, and at this point the system response is very rapid. Okay, so this is because of the overall stiffness of the system. Again, you have slow time scale and then a very rapid time scale, slow time scale, then a very rapid time scale. So as you can see over here in this practical example also, you have case where a slow time scale is mixed with a fast time scale. So with that, I come to the end of this lecture. What I have covered in this lecture, ODE-45 and ODE-15s. ODE-45 is a Runge-Kutta explicit solver. If you know a priori that the system is a stiff system, you may want to use ODE-15s instead. If you do not know whether the system is stiff or not, it's always a good idea to first try ODE-45. If ODE-45 does not work, then you would switch to ODE-15s. So with that, I come to the end of this lecture and I will see you in the next lecture. Thanks.